to introduce the first speaker, Andrew Childs, who will talk about a problem that actually he proposed at one of the brainstorming sessions of the Simons program last spring, and some nice discussion followed it up, and then the result, which we will hear about, is symmetries, graph properties, and quantum speedups.
Yeah, thanks very much, Anders. So it's a pleasure to be able to tell you about some of this work. Yeah, so this is joint work indeed with Anders, along with my other co-authors, Shalev Ben David, William Kretschmer, Siddhartha Potter, and Daochen Wang. And some of this work was done kind of separately from the Simons program, but as Anders mentioned, some of it was done kind of in response to an open problem session that we had there during the program, and it was really great to have the chance to talk with Anders about it there, and to really make some progress actually on this question. So I'm going to tell you about sort of the plan is to kind of tell you about the context for the work in general, and sort of the setting that we care about, and sort of say what the main results are, but then to give a little bit more detail on the particular stuff that we actually worked on, there at Simons, although maybe not that much detail, but we can always sort of, follow up with some discussion later. And there's a preprint that gives a lot of details, if you're interested in reading it. I would recommend you go there. Okay, so the kind of general question that we're interested in, is this question about the power of quantum computers. And I think I don't have to really introduce this, very much to this audience. It's really a kind of a basic question about quantum computers to understand, what are the problems for which they can give us significant speed up. And as you know, there are some problems for which we can get exponential speed up, or we think we can get, exponential or at least super polynomial speed up over the best classical algorithms. And in some cases, depending on the model, we can even prove that we get exponential speed up. And on the other hand, there are other kinds of problems for which we get, some speed up maybe, but only polynomial speed up. Of course, there maybe are some other problems for which we don't get any, significant speed up at all. But a really basic question is why is it like this? What is the reason for some problems having this very significant speed up and others, not having significant speed up? Somehow, we need a problem for which we can organize the interference in a quantum computer in such a way that it allows us to find the solution quickly. And somehow that's not a feature that we can take advantage of with a classical computer. So, I think there's kind of a general understanding now that problems have to have a lot of structure for quantum computers to be able to take advantage of that structure to get significant speed up. And sort of the goal of this work is to try to, make that more precise, to try to understand better, what are the kinds of structures that allow for significant quantum speed up. Okay, and we're going to consider this question in the setting of query complexity, which, I think this model is probably familiar to many of you, but this is a useful model for exploring the relative power of classical and quantum computers, because partially because it's feasible to prove lower bounds in this model. So in this model, the input is described by a black box that somehow has some string, hiding within it, but you're not allowed to directly, just kind of read that string. You're not just given the whole string. Rather, you have to make queries to the black box to learn anything about the string. So what you can do is you can query a particular specified character of the string, and the black box will tell you what is the value at that position of the string. And on a quantum computer, you can do this in quantum superposition in sort of the standard way. And then the question we're interested in is how many times do we have to query, how many positions of this string do we have to query before we can learn some property of the input? And in this talk, we're just going to be interested in sort of, answering yes/no questions about the black box input. Okay, now we can define, sort of different versions of this notion of query complexity depending upon the specific model of computation that we care about. And, in particular, we can use this model to compare classical and quantum models of computation. For this talk, we're mainly going to be interested in the relationship between the randomized classical query complexity and the quantum query complexity, both with bounded error. Okay, so, just, a very kind of common example that I'm sure you're familiar with is the unstructured search problem, where we want to compute the logical OR of the bits. If we've got some n-bit string and we want to know the logical OR of the bits of that string, this is a problem for which we can get a quadratic improvement of the quantum query complexity over the classical query complexity, whether it's deterministic or randomized. All right. So we're also going to be interested in sort of the setting of promise problems. So in the unstructured search problem, there's no promise, but in general, we're going to be interested in problems for which there might be some promise that the input comes from some specific set. And this slide will also maybe hopefully will help to set some of the notation for the talk. So we're going to be given an input string X specified again by a black box. That's, it's an N character string over some alphabet sigma, but it's not necessarily an arbitrary string over sigma. Rather, it's going to come from some set P that could be much smaller. So P is the promise set. We're promised that the input comes from the set P. And now a query to the black box involves specifying an index I from 1 through N, and then the black box will tell you what is X sub I. And our goal is going to be to compute some function f of X, where f maps elements of this promise set to 0, 1. Okay, and we want to do this using as few queries as possible. All right, so if there isn't a non-trivial promise, in other words, if X could be a completely arbitrary string over sigma, so P is equal to sigma to the N, then we say that f is a total function. And otherwise, we'll say that it's a partial function, or that we have a promise problem. There's some non-trivial promise that we're told that X comes from some specific subset P. And this can really significantly affect the difficulty of the problem. So if P is special, then the problem could be a lot easier than if P is sigma to the N. In particular, it's a well-known result that if f is a total function, then you can have at most a polynomial speedup of quantum over classical computation. So it's now known, I guess, that you can have at most a 4th power speedup. And so what this tells us is that promises are really necessary for exponential quantum speedup. We can't have exponential speedup for total functions. We have to have a promise. Okay, but just having some promise is not enough, of course. It matters what the promise is, right? If the promise is somehow, there's one input that's excluded, that's not going to help so much. And in particular, and more than that, there are, properties of promises that are going to be sort of more or less helpful. And so we would like to understand more about this. What are sort of, promises that might allow for exponential quantum speedup? So an example that sort of illustrates this nicely, I think, and that's, relevant to the kind of properties that we're going to be looking at in this talk, is the sort of relationship between the collision problem and Simon's problem. So in the collision problem, we're going to be given an input X over, so X is an N character string over some alphabet sigma. Now sigma can't be just 0, 1 for this problem. Sigma has to be a larger alphabet. Like it has to have size at least like on the order of N for this problem to be well defined. And so here's the promise. So I'm sort of defining what this set P is. X can either be a 1-to-1 string, which means that every character of the string is distinct, or it can be a 2-to-1 string. And that means that the characters of that string come in pairs. Every sort of, character that appears in the string appears exactly twice. And so then we would say the string is 2-to-1. And the collision problem asks us to distinguish these two cases. Do we have a 1-to-1 or a 2-to-1 string? And, it's well known that there is polynomial quantum speedup for this problem, but only polynomial quantum speedup. So classically, you can do it with like square root of n randomized queries. Quantumly, you can get by with n to the 1/3, and that's the best you can do by sort of this well-known collision lower bound of Aronson and Shi. Okay, so that's an example with polynomial quantum speedup. Now notice that there is a promise in this problem, right? The X is promised to be either 1-to-1 or 2-to-1. That's very special, right? I mean, most strings are neither 1-to-1 nor 2-to-1. But here there's the promise. Although it's a very non-trivial promise, it's not somehow a promise that has the right kind of structure to allow for exponential quantum speedup. But another example that sort of like gives a sort of subset of the instances of the collision problem is what's called Simon's problem. So in Simon's problem, we're going to do something, we're going to introduce some further structure. So let's identify the indices of X, so these indices I, with strings of log n bits. And then the promise is going to be either that, the function is 1-to-1, or it's 2-to-1, but it's 2-to-1 in a very particular way. So it's 2-to-1 where the pairs of characters in the string that are the same have indices that are related by XORing with some fixed string of log n bits, right? So there's some, there's some like fixed string S that somehow you use to relate the indices of, positions in the string where the character is the same, right? So those are the sort of the yes instances of the problem, and the no instances are the one-to-one, the arbitrary one-to-one strings, right? So, this is an even more special promise. And it turns out that this promise is enough to allow for exponential quantum speedup, right? So it turns out that classically the query complexity is basically the same. Like a classical computer can't really, make anything out of this promise, but a quantum computer can, and it takes the query complexity all the way down to like logarithmic, right? So there's now an exponential gap between the classical and the quantum query complexity. So what's going on here, or one thing that's going on here, is that in the collision problem, the problem is permutation symmetric. Like the promise set as well as the function are permutation symmetric. It doesn't matter how you order the indices, but this bit structure to these indices that's been imposed in Simon's problem is, makes the problem not permutation symmetric, and you have this like very highly structured promise. So that's a relevant fact, and it's sort of related to something much more general that's true, which is this kind of permutation symmetry is always enough to prevent exponential quantum speedup. Okay, so that's kind of the principle here, that symmetry can prevent quantum speedup, and this is really quite a general thing. So let me say that a function is permutation invariant if for any permutation of the indices, so any pi in Sn. The promise set is permutation symmetric in the sense that for any x in the promise set, x with its indices permuted by pi, that's what I mean here by x composed of pi, that's also going to be an element of the promise set. So this is just saying that the promise set is permutation symmetric. And furthermore, the function value is the same if I permute the indices according to any permutation, right? So the collision problem is permutation symmetric in this sense. And it's a theorem that for any permutation invariant problem, the quantum and randomized query complexities differ by at most a third power. So this was shown by Chailloux, improving an earlier result of Aronson and Abinas. And so I think this raises a kind of a very natural question, which is, what about other symmetries, right? So this is about like full permutation symmetry, but what if you have less symmetry than that? What is sort of, enough symmetry that is, significant enough to prevent exponential quantum speedup? I mean, first of all, are there any symmetries other than the full permutation symmetry that are enough to prevent exponential quantum speedup? And, if so, what are they? And, I think this is a nice question from the standpoint of looking for, quantum algorithms, because, we would like to know sort of, what to avoid, right? I mean, what are the things that will prevent exponential quantum speedup? That sort of tells us where not to look for exponential quantum speedups. Okay, and a kind of particular motivating symmetry that's going to be sort of like the main it's going to be a sort of an important object in this work is this notion of graph symmetry. And maybe this also helps to give an example of sort of a symmetry that's less than full permutation symmetry that would be of interest. So so we're going to call a problem a graph property if the input describes a graph. So it's going to say basically what edges are present in the graph. We've got n vertices, and the input tells us what edges are there. And then the property depends only on the isomorphism class of the graph, right? So we have n vertices. You could imagine specifying the graph by like, you have these vertices numbered 1 through n, and then the input just tells you which pairs of vertices are adjacent. But to be a graph property, it should sort of only depend on the picture. It shouldn't depend on how the vertices are numbered, right? It should only depend on the isomorphism class. And so, this is just sort of the same thing kind of written out algebraically, right? So, but the input, again, just specifies what edges are present in the graph. So, when I think about permuting the vertices in some way, right, that's a permutation of n things, but the input has sort of like n choose 2 bits in it, right? So those n choose 2 things, these bits that are telling us whether an edge is present or not, those are getting permuted in some way that's carried over from the permutation of the vertices, right? Specifically, like the way I permute the edge uv is that uv gets mapped to pi of u comma pi of v, right? So there's only like n factorial permutations of the of the vertices, but there's like, there would be like n choose 2 factorial ways of permuting, the bits that specify all of the edges. So somehow this is really much less than like full, full symmetry of the input. It's a very special kind of class of symmetries. Okay. Okay, good. So, so we're going to be interested in sort of what we can say about the query complexity of graph properties that have this, kind of much smaller symmetry group. And we're also going to be interested in a sort of another thing about the way we could define the promise in the problem, which is in the setting of property testing. So in property testing, we have some property that on yes instances is going to be satisfied, but then we have some additional feature of the promise, which is that if you're a no instance, you should be very far from any yes instance, right? So in property testing, and this is like a fairly strong thing and can sometimes allow for much faster algorithms, right? So you either have a yes instance or you're promised that your instance is very far from any yes instance, right? So we could talk about, for example, like, we're given some graph that's either a bipartite graph or it's very far from a bipartite graph, meaning you would have to change many of the edges to make it bipartite. And then you can ask something about the cost of testing that property on a black box input. And actually this setting has been widely studied in, classical as well as quantum computing. And it was shown, for example, by Goldreich and Ron, that, there are some problems for which, I should say, like for many problems, actually, you can do things really dramatically faster in this property testing scenario than if you didn't have this big gap between yes and no instances. But there are some problems for which you don't get such a significant advantage, when you try to test, at least classically. And so, for example, if you're given a graph as specified by an adjacency list representation, and let's say it's a bounded degree graph, so for every vertex, it can have at most a constant number of other neighbors, let's say, then they showed that the randomized query complexity of testing a property like bipartiteness is like the square root of n. They actually showed this also for testing expansion. And so we did some work on this quite some time ago now, where we considered quantum algorithms for these properties in the same setting. And we showed that actually for these two problems of testing bipartiteness and testing expansion, we could get a polynomial quantum speedup, so taking things down from the square root of n to the cube root of n. And actually we showed that you could get at most a polynomial speedup, although we still don't know how much speedup is possible, for the problem of testing expansion. And actually, we still don't know for bipartiteness. Like, we don't have a proof that you can't get an exponential, quantum speedup for testing bipartiteness in the adjacency list model. But this result about testing expansion, kind of suggests, I don't know, maybe these are problems for which you can get only polynomial quantum speedup, right? That's the case here. And maybe that's true kind of more generally because of the nature of the symmetry of these problems, right? So, maybe we could rule out testing, getting an exponential speedup for testing bipartiteness in that way. And maybe more generally, maybe it's never possible to get exponential quantum speedup for, for testing graph properties because of the sort of, symmetry of these problems. And so we sort of, I guess, maybe kind of like implicitly posed this question, and it was also mentioned in this paper of Montanaro and de Wolf, this nice survey article that they wrote in 2013. So one thing that I want to emphasize is that there are sort of different models of access to a graph. So here we're talking about the adjacency list representation, but you can also have other natural models. Like, one that's used very often is the adjacency matrix representation, where there's a bit that specifies for any given pair of vertices whether they're adjacent or not. And that's the adjacency matrix representation. And the answer could be quite different depending upon which representation you take. And actually, this is sort of the case, as we'll see. Okay, so let me now sort of summarize what the main results are, and then, as I said, I want to sort of take the spend the most time focusing on one of these three results. That's the one that we worked on there at the Simons Institute. Okay, so the first thing we show is that actually in the adjacency matrix model, right, where the black box describes basically the adjacency matrix, right? So we have this like n by n adjacency matrix. There's a bit for every pair of vertices that tells you whether those two vertices are adjacent or not. Then you can have at most a 6th power speed up of quantum over classical query complexity, over the randomized query complexity. And in fact, more generally than this, we show that you can have at most a power 3k speed up for k uniform hypergraph properties, right? So k equals 2 is the the sort of case of graphs. K equals 1, I guess, is the sort of fully symmetric case that was sort of already handled by Chailloux. But you can also consider 3 regular hypergraphs, 4 regular hypergraphs, et cetera. The bound gets looser and looser, but anyway, this is what we show. And so this shows that in some sense, this is another class of symmetries that prevent exponential quantum speedup, right? Graph properties are somehow, still enough, even though there's much less symmetry than full permutation symmetry, it's still enough, to prevent exponential quantum speedup. We also show that in some sense, and we don't sort of like kind of completely show this, but we sort of go some way towards showing that in some sense, this is like the only way of preventing exponential quantum speedup with symmetry. And so we do this by sort of considering more general permutation groups that could be the symmetries of functions that you might want to compute in query complexity. And we show that for a class of permutation groups that are what's called primitive, that you can sort of characterize whether speedup is or is not possible in terms of a property of those permutation groups called its base size. And we sort of show that if the base size is in some sense large, you can have at most polynomial quantum speedup. If it's small, then it's possible to have speedup. There exists a function that has super polynomial quantum speedup. And furthermore, you can sort of show that this large case kind of the only way that this can happen is to have a hypergraph symmetry. So in some sense, the only symmetries that prevent significant speedup are these hypergraph symmetries. Now, this is just for primitive permutation groups, which are in some sense building blocks of general permutation groups, but somehow, if you look in detail at the way that they can be used to compose general permutation groups, the thing that we show is not quite enough to kind of fully characterize speedups for general permutation groups, but it's somehow close. There's a nice open question there to somehow complete this classification. Okay, but then the sort of last of our results looks at the case of the adjacency list model, right? So this result is about the adjacency matrix model, but what if instead we have, let's say, a bounded degree graph that's specified by an adjacency list, right? So in the adjacency list model, you can specify to the black box a particular vertex that you care about, and the black box will tell you what are its neighbors. Either you sort of give the index of one of its neighbors, and the black box tells you what is the neighbor with that index, or maybe if we're talking about bounded degree graphs, it's the same up to a constant factor to just say that the black box tells you all of the neighbors. What we're interested in is also what is the quantum query complexity of graph properties in this adjacency list model, because, for example, we would like to understand the quantum query complexity of testing bipartiteness or testing expansion, which are problems that are defined in this setting. What we show is that actually it is possible to get exponential speedups in this model. And in fact, it's even possible to get exponential speedups in the setting of property testing, right? So in property testing, you have this like very strong promise that the property, whatever it is either satisfied or it's far from being satisfied, right? Which again means that you have to change a large fraction of the edges if you're given a no instance to turn it into a yes instance, right? So that's a very strong property, which means that in some sense you can have, you would expect to be able to have pretty fast classical algorithms as well as quantum algorithms. But it turns out that, somehow you can still have a big gap, right? So we give an example of a problem that, that has such an exponential quantum speedup. And so this is the thing that sort of, I kind of discussed in the open problem session at the Simons meeting. We sort of knew that this was possible for graph properties generally, but it was unclear whether you could sort of have a graph property testing problem for which this was the case. But it turns out that even that is true, that even for graph property testing in the adjacency list model, you can have an exponential quantum speedup. Okay. So that's those are sort of the main results. And what I want to do in the rest of the time is just talk a little bit about this last result. But I don't know, maybe this is a good point to maybe just pause just to see if there's any questions to clarify the setting or what the results are. If there's any questions, I'm happy to answer them.
So very quick question, Andrew.
Yeah.
So the full permutation symmetry, what does it correspond to in this picture? Is it complete graph or something like that?
So if you're talking about graph properties, then like full permutation symmetry simply doesn't arise, right? I mean, the permutations act on the vertices, and a permutation of the vertices induces a structured permutation of the possible edges, right? So there's like, n factorial ways of permuting the vertices. But whether the graph is the complete graph or it's some very sparse graph, still the way the sort of edges or non-edges would be permuted is the same, right? That somehow uv gets mapped to pi of u pi of v, and if it's the complete graph, okay, that's always there. But the symmetry is like, it's not a property of the graph as such. It's a property of the, because you don't know what the graph is. I mean, the graph could maybe be anything. It's a property of the, the fact that we're talking about graph properties, right? I don't know if that helps.
That is, thanks.
Okay, great. Awesome. Okay, great. So yeah, maybe I'll go on and just tell you a little bit about this, this problem of sort of showing an exponential separation for a graph property testing problem in the adjacency list model, right? In the adjacency matrix model, we showed that that's not possible, but in the adjacency list model, we showed that it is. And I'm going to talk a little bit about how we're able to show that it's possible. Okay, so the kind of main tool in showing this is this, maybe the seed for constructing an example that shows this is this example of exponential speed up by quantum walk from a rather old paper that we wrote. And the idea of this example is to sort of show that quantum analogs of random walks, these coherent quantum walks on graphs, can solve some problems dramatically faster than is possible, with any classical algorithm. So in this paper, we defined this, so-called welded trees problem, where we're given an adjacency list black box for a graph that looks like this. We have two binary trees that are joined together by this weld. That's like a random cycle that alternates between the leaves of the two trees and eventually comes back to where it started, so that every vertex here, except for the entrance and the exit, every vertex has degree 3. And so locally, the graph kind of looks like, just a 3 regular binary tree. There are, of course, cycles if you go to sort of like large enough scales. There can even be small cycles, but they're sort of rare. Anyway, so the graph, has this structure. And now the question is, given an adjacency list black box for this thing, and given, initially the entrance, find the exit, right? You want to somehow find your way through this graph to the exit vertex. And you can imagine that the way that this adjacency list black box refers to the vertices is that it gives them names that are much longer than you would need to sort of minimally specify them. So you can really only hope to explore the graph locally. Like if you start from the entrance, if you just come up with some random name, it's probably not the name of any vertex, right? So really all you can do is sort of use this adjacency list black box to explore the graph locally. And now, you want to understand how fast it is, how fast you can find the exit. And so for a, with a quantum algorithm, you can run a quantum walk on this graph, which is some coherent quantum process that you can show will find this exit vertex in polynomial time. Okay, but on the other hand, a randomized classical algorithm, you can prove, needs exponential time to find the exit. Basically, because to a classical algorithm, this graph kind of looks like an infinite binary tree. Somehow it can never get oriented. It never gets any information that allows it to sort of, move in the right direction of the exit. So this, this sounds like actually a lot like what I'm talking about, right? Because there's an adjacency list black box and there's an exponential separation, right? But this is not an example of an exponential separation for a graph property, because we've given you sort of an entrance point into the graph, right? We've specified a particular vertex of the graph, and so we've sort of broken the symmetry by doing that, right? The graph property really sort of depends in some way on how the vertices are labeled. So how do we sort of modify this so that it's actually a graph property? Well, so there's a kind of a fairly straightforward way of turning this into an exponential speedup for a graph property by just modifying the instance a little bit. What you can do is somehow like decorate the entrance with some large binary tree that if you choose, you know, a random vertex of the graph, like you'll probably find something over here. And then, you know, from this thing, you can create, you can sort of like find your way to the entrance, and then you can run the ordinary, you know, quantum walk algorithm to find your way to the exit. But, you know, if you have a classical algorithm, then it's going to be hard for sort of like the same reason that it was hard in the original case. So yeah, maybe in the interest of time, because I see like we're supposed to only go for half an hour. Yeah, let me not sort of read all these words, but just say, I mean, I think I already said what the main idea is, that by somehow, you know, expanding the graph a little bit, you can make it an ordinary graph property. So you're not given the name of this entrance vertex or of any particular vertex. You're just given an adjacency list black box for this graph. But nevertheless, you can sort of come up with a quantum algorithm that will sort of distinguish the two classes of graphs, you know, fast, whereas classically you'll still need exponential time to distinguish them. However, and so this is where things sort of were at the beginning of the open problem session there at the Simons Institute. This is a graph property now, but it's not a graph property testing problem, because you know, what we define here are two classes of instances that are very close to each other, right? We're going to consider here, we're just going to change things locally at the exit by either adding or not adding these three marker vertices. So you can change just these three edges to change between yes and no instances, right? So this is not a graph property testing problem, even though it's a graph property. And so what we want to do to make this problem, you know, into a graph property testing problem is to come up with some kind of a structure that can still be, you know, sort of efficiently understood by a quantum algorithm, but so that a classical algorithm will still have a hard time distinguishing things, you know, even when it's given the promise that the no instances are very far from the yes instances, right? So you're not allowed to have these like instances that are hard to distinguish from the yes instances only because you changed, you know, a few vertices in sort of a small place. And so the sort of construction that we use sort of builds upon this welded trees idea, but by taking many copies of these welded tree graphs with these antennas, these large binary trees attached to the two roots, and then with some additional edges added to somehow, you know, provide some advice that sort of tells you about whether a vertex is in what we call the body, this sort of central thing, or is in one of these antennas, these binary trees that are added to the left and to the right. So I don't know, how strict are we being on time, Anders? Can I just take like sort of 2 or 3 minutes to say a few more words about this?
Yeah, a few minutes should be fine. We already
Okay.
had 2 questions.
Okay, great. All right, thanks. Okay, yeah, so let me just say a few words about sort of the two main sides of this. One is to show that quantumly, you know, we can sort of distinguish the yes and the no instances. And the other is that, you know, classically it's hard, right? So on the sort of quantum side, that we sort of consider this setting where you're given this untrusted advice that sort of tells you whether a vertex is what we call a weld vertex. So that's a vertex, you know, right here in the middle. It's at the place where the two binary trees are welded together, or not. And that information is encoded in, you know, so there are these edges that are added. They're sort of special edges. They're like, we have like two parallel edges that are added between vertices between an antenna and a body. And they're going to be connected to an instance of this graph that has a parity of these. So there are these circles that you see here at these root vertices. The parity is either going to be even or odd, depending upon whether you connect to something that's a weld or a non-weld vertex. So this is some way of encoding in the structure of the graph, you know, some advice that's going to tell you something about whether you're a weld or a non-weld vertex. Now, if you would have that advice and you would really be able to know what that advice says, then even a classical computer would be able to test the property of whether you have an instance that looks like this or whether you're far from an instance that looks like this, right? So, you know, we sort of define some tests that these are just classical tests that kind of use non-backtracking walks to sort of check that certain properties of the graph hold. Such that, you know, like yes instances of the problem will definitely pass and no instances are likely to be detected. Okay, so you could even do this classically if you had this advice. But the thing is, you're not going to have this advice given to you directly. I mean, there's no advice in this problem anyway. And the advice is really just encoded in the presence of these edges, these advice edges. And these are edges that can be used by a quantum algorithm, because using the ability to sort of solve this glued trees problem, you can sort of make use of these edges to figure out whether you have a weld or a non-weld vertex, and then you can use that information in this kind of classical test with advice. And so quantumly, you can sort of unlock the advice and make use of it, but classically you can't. And so, like, well, certainly it's not obvious how to run this tester and solve the problem. But what we show is that actually the problem is really hard. Like, not only can you not unlock the advice, but the problem really still takes exponential time classically. And the way that we show this is basically by constructing some specific set of no instances where we just sort of self-weld the binary trees. These are instances that are legitimate no instances. They're far from any yes instance. And we show that even these specific no instances are hard for a classical computer to distinguish from the legitimate yes instances. And this basically follows by sort of the same kind of hardness argument that we give for the for the ordinary glued trees problem. Okay, so I'm a little bit over time. Let me maybe just stop there, but say that there are still lots of open problems related to this. There are some interesting open questions about sort of the sort of adjacency matrix type stuff, kind of understanding what the best possible separations are for various kinds of problems. And as I mentioned, there's this problem about sort of characterizing the permutation groups that allow for super polynomial speedup, which we don't yet kind of really fully characterize. And I think there are also some nice questions related to this adjacency list, stuff that I sort of talked about at the end. The problem that I described is, of course, completely artificial and contrived to show a separation. I think it's a nice question to sort of think about whether this kind of thing could lead to an actually, useful quantum algorithm. In particular, the problem of testing bipartiteness in the adjacency list model is still open. I think it would be very surprising if there were an exponential speed up for that problem, but actually showing, one way or the other, I think would be really nice. And sort of in general, better understanding, what are the kinds of graph property testing problems for which we can or cannot have exponential speedups is, I think, a nice question. Okay, sorry to go a bit over, and let me stop there.
Thank you for the talk. Now we have a few minutes for questions. So please speak up if you have a question.
I have a question.
Sure.
In your open problem for k strictly greater than 1, what is p?
Oh, sorry. This is probably for, what is p? That is a good question. Maybe this is meant to be k? I'm actually not sure off the top of my head what I meant by that.
I think it is K. I'm not entirely sure.
Yeah.
I also think that we can actually improve this now using the recent, there's the work by Shirstov and Wu, which gives a larger query complexity separation. So it might be more like p to the 1 minus epsilon or something.
Okay.
Or I guess k to the 1 minus epsilon, but I'm not entirely sure.
Yeah. I think this p is k. This is for like, I think at one point in our paper we talked about p uniform hypergraphs. So it's yeah, sorry for the confusion. I guess this p is k. Yeah, but that's interesting, I guess. But this is, I guess, like a fairly small improvement, I guess, right? I mean, I guess there's still quite a large gap between sort of the best separations that we know and the sort of the lower bound.
There's a question in Q&A by Rona. What prevents any speed up for adjacency matrix model?
Is the question is about like the mechanism for preventing the speed up? I mean, I guess.
Let me make Ron a panelist. Just maybe question directly. Just one sec.
I mean, it's
Sorry,
yeah.
I think
If the question, if the
was
there's a
raised
little bit of
wrong.
echo. If the question is, yeah, sort of like what is the mechanism for preventing the speed up? I think it's like, I don't know. I mean, what is preventing the speed up is the symmetry. And you know, I mean, if the question is about what the proof looks like, I guess it's you know, it essentially is a generalization of the sort of like the k=1 proof. You know, we sort of use sort of Chaillou's method, but sort of show how you can sort of like effectively embed the yeah, the sort of like full permutation symmetry, but with some loss, you know, into the kind of setting where you have, let's say, a graph symmetry or a hypergraph symmetry. But I don't know if that's really a satisfying answer to the question.
Okay, thank you. I think that helps.
Okay, all right, thanks.
Do you have conjecture k=1 case?
You're asking here whether it should be where it should be between 3 and 2?
That's right.
You probably know better than I do. I don't know. I mean, I don't think I have an informed conjecture. I mean, you know, I guess there was, you know, I guess there was all this sort of like, you know, for sort of like, I guess for total functions, there was this, you know, question about whether you could have, you know, superquadratic speedups. And I guess you and others worked on this and sort of showed, you know, examples of, you know, of superquadratic speedups, which was, I guess, surprising at the time. So I guess if the same thing plays out in this context, you know, maybe, I don't know, maybe you can do better than this, but it's a different setting. So maybe, yeah, I really just don't know. I don't have any intuition for this really.
Okay, thanks.
I wanted to ask about the status of monotone graph properties. Like, do we know any partial results, at least in this direction?
No, I don't think so. I mean, I guess what would a partial result look like? I mean, I guess this is, you know, I guess the reason that maybe we you know, be interesting to think about monotone graph properties is that, you know, I guess bipartiteness, or maybe you have to think about non-bipartiteness. But anyway, you can sort of have a sort of a monotone graph property, and maybe this could be maybe, you know, a way of somehow, you know, showing, and I guess also for expansion, right? I mean, I guess it again has this issue that this you know, kind of a character that somehow if you add edges, you can only make the graph, you know, kind of more expanding. So maybe that could be sort of a feature that sort of like distinguishes, you know, these kind of, you know, wacky cases. You know, certainly the thing that we constructed is non-monotone, and maybe that could be the thing that you know, distinguishes it from you know, more pedestrian things like bipartiteness and expansion. But I think that's, I don't think there's anything more that we know about that. I mean, I suppose another thing is just to look, you know, one could do is just to look at specific examples of monotone graph properties and try to understand, you know, the classical and quantum query complexity of testing them. You know, the sort of the lower bound for testing expansion, you know, quantumly is really like, you know, not at all straightforward and uses like very specific properties of expansion. So something that sort of, you know, considered, let's say monotone properties more generally would have to look presumably very different.
So there's a question in Q&A.
Yes, I see. Yeah, thank you. So to connect the permutation symmetry to physical systems, is the permutation symmetry in the total wave function of indistinguishable particles a reason that prevents exponential quantum speedups for electronic structure problems? I mean, I don't know of a connection along those lines. I mean, I guess the yeah, I mean, in the sort of, stuff that I talked about here, the symmetry is a symmetry sort of the input, whereas in the electronic structure problems, it's like a sort of, underlying property of the quantum state. It's like a property of the state space that the thing that you're looking for lives in. So I think it's really quite different. I guess I don't really see a connection between these two things. If there were one, it would be really interesting.
Okay, well, thank you, Andrew, once again. In the interest of time, let's to keep on the schedule. Let's move to Robin's talk. Robin. So yeah, it's our next speaker is Robin.